The first gas law we're going to be talking about is Boyle's law. Now, Boyle's law was developed by a man named Robert Boyle in England, and we're going to see a bunch of these laws developed by a bunch of people at the exact same time. They were all working on gases simultaneously, but they were taking it in slightly different directions. Boyle, what he did was he compared pressure and volume of a gas, and what he found was the pressure of a gas, symbolized P, is inversely proportional to volume. Okay, so we have to think about math class for a second. Proportional means that the change is going to be the same. So whatever one does, the other one does. But the key here is the word inversely. Inversely means opposites. So what's going to happen here, as pressure and volume change, they're going to change in opposite directions, but they're going to change by exactly the same factor. So if you double your pressure, then your volume will go down by exactly the inverse of 2, which is 1/2. So it'll go down by a half. So we're going to look at these changes as we're going through, and this is really important because this is the one law that's really different from all the other ones by the fact that it's inversely proportional. The other ones, as you will see soon, are directly proportional, meaning they change in the same direction by the same amount. So always remember, this is the key statement here. Pressure and volume are opposites to each other. How do we calculate it? Simple. We're going to use this formula. P1 over P2 equals V2 over V1. Now, when we do this, it says all other factors are held constant, which means temperature and moles are going to be held constant. So in other words, we're not going to change how much of it, and we're not going to change the temperature of the molecules, how much energy they've got. Now, the 1s and the 2s means this is where it starts, and the 2 means where it ends. Okay? So, starting pressure, ending pressure, starting volume, ending volume. And notice that the 1s and the 2s are opposite to each other. 1 is on the top, 1's on the bottom, bottom, top, etc. Let's do an example problem. A sample of hydrogen gas is at 1 atmosphere and a volume of 22.4 liters L. What pressure would the gas have if the volume dropped to 11.2 liters? Now, because we're dealing with a mathematical problem, I know your first reaction is, oh, he's going to say, what's the first thing we do? And that's true. And you're going to say, write the given. The problem is, I have a bunch of givens, and they mean different things. So now that we actually have a mathematical formula to work with, the first thing you should always do is write your formula. Okay, so P1 over P2 equals V2 over V1. Now, in the beginning, until you get good at this, I would list out what you know. What do I know? Well, I know the pressure of, I know P1, because it says a sample of hydrogen gas is at 1 atmosphere. So my pressure is 1 atmosphere. P2 is whatever the new pressure is going to be. So it says, what pressure would the gas have? Means I'm looking for the pressure. My volumes are going to connect with whatever my pressures were. So it says it's at 1 atmosphere and a volume of 22.4 liters. So my volume 1 is 22.4 liters. The volume is going to change to 11.2 liters. So my V2 is going to be 11.2. Now I have all the information I need to know. I know what I'm solving for, so I'm going to plug it into my formula. P1 is 1, V2 is 11.2, V1 is 22.4, and I'm solving for P2. Okay, so I've got a ratio basically. I've got two fractions. Well, how do I solve? I cross multiply. Okay, multiply 11.2 by P2, 22.4 by 1. Solve for P2 by dividing what's connected to the variable. And bam, I get an answer of 2 atmospheres, which makes sense. If you look at the volume, if you look at these two situations, as the volume went from V1 up to V2, it went down by a half, which means that the pressure should go up, should double. Okay? And of course, I circle my answer at the end so that the teacher can clearly find it. Go away. Okay. Here's my next example. A sample of CO2 gas has a pressure of 5.65 atmospheres in a 125 milliliter flask. The sample is transferred to a new flask where it has a pressure of 6.99 atmospheres at the same temperature. What is the volume of the new flask? Of course, the first thing we do is write down what we're given. So, we write our formula. So P1 over P2 equals V2 over V1, and list out what we know. P1 is 5.65 atmospheres. P2 is my second pressure, 6.99 atmospheres. V1 is whatever's connected with the 5.65, which is 125 milliliters. V2 is it says what is the volume, so that's what I'm solving for. Now you'll notice that the units changed in this problem. Last problem it was liters for volume. This time it's milliliters. Units are not really important until we get to one of the later formulas. As long as your units are the same from start to end, it doesn't matter what units you work with, like atmospheres, torrs, millimeters of mercury, milliliters or liters, etc. It does not matter what you're working with. So now I plug my numbers into my formula. 5.65, 6.99, V2, and 125. So now I take out my handy dandy calculator and I solve. So I cross multiply 5.65 times 125 equals, divide by what's connected to my variable, 6.99, and I get an answer of 101.04. And of course, I look at my significant figures, and I see I have 3 sig figs, 3 sig figs, and 3 sig figs. So my answer will be 101 milliliters. Again, to figure out what units you have, just look at the other thing that is connected. So I'm solving for volume. So I look at the first volume, and I can see what my units are going to be. Let's do one more example. What would you expect the volume of a 3-liter sample of helium to be if its pressure is increased from 1.5 atmospheres to 2.0 atmospheres? Again, I know it's a Boyle's Law problem. So I write down my formula, write down what you know. My pressure is 1.50 atmospheres to start. It changes to 2.0 atmospheres. My volume when I started was 3.00 liters. It asked me for what the new volume will be. So I'm solving for V2. Plug in your numbers. And cross multiply. And again, we're going to solve for V2. So let's clear out those. So I go 1.50 times 3.00, enter, divided by 2, and I get 2.25. But of course, I have a change in sig figs. I have only 2 sig figs here, so my answer will be in 2.3 liters. And again, the beautiful part about gases is you can always ask yourself, does my answer make sense? If you look at the pressure went up. If the pressure goes up and volume is inversely proportional to pressure, my volume had better go down. Well, my volume started at 3, it went down to 2.3. I don't know if my number's right, but at least it makes sense, and that's the key.